Hello everyone, I wanted to look at the 2025 AP Chem free response together. So the answer key is not released yet, so please keep in mind that this video is my interpretation of these questions and it may not be perfectly correct. There may be discrepancies on the answer key when it's released, so please check there later to verify, and if you think I made a mistake, please also let me know in the comments. In question 7a, I'm shown a Lewis dot diagram of glycolate the ion, and I'm being asked to determine and circle the atom that accepts the proton. A proton is an H+, and what I'm going to look for is the negative part of the ion, which is this part, COO-. So that part is negative, so that's going to have the attraction to the H+ to form COOH, which you may recognize as a functional group. That's carboxylic acid. So which oxygen is going to take the H? So it's this one, because if you were to sketch the Lewis structure of COOH, it would be this oxygen that I circled with the H beside it. In question B, I'm being asked to determine what is the Kb value, so the equilibrium or the base ionization constant for for the glycolate ion. So I rewrote the equation above. There's not a ton of room to write. That's fine. I'm going to set up an ice table, and I'm going to use my ice box because in my Kb expression, these concentrations have to be at equilibrium. So the water we can omit because we don't take the concentration of, it's just a pure liquid. So if I read question B, I'm starting with a 2.5 mole per liter solution of glycolate. And then for my hydroxide, it'll be 0, and my conjugate acid is also 0 as they're products. Products always start at 0. Now, reactants will decrease by X, or their mole ratio. Products will increase by X, or their mole ratio. But it tells me here that hydroxide, this is how much I have at equilibrium, 1.3 times 10 to the negative 5 moles per liter. So that is my X value, okay, because this all reacts in a 1-to-1 to 1-to-1 mole ratio. So I'm just going to put this value in for my icebox here. So that means for the glycolic acid, the conjugate, it's the same thing. So it'll increase by the same thing, and I'll have the same amount at equilibrium. And that means my glycolate will decrease by 1.3 times 10 to the minus 5 m. Remember that reactants will always decrease and products will always increase, and that will give me 2.499. Okay, so now I'm going to plug these equilibrium values into my Kb expression to calculate Kb. Let me just try to clean this up a little bit. Again, I don't have a ton of space to write, so hopefully you can follow me. So let's plug these values in. So Kb equals the concentration of products divided by concentration of reactants raised to their mole ratios, but again, it's a 1-to-1. And then, okay, so those are my products, and my reactant is 2.499. So when you do all this, you get Kb equals, so I think we should be rounding this to 2 significant digits, because yeah, in the question it looks like we're given 2. So we're going to round this to 6.8 times 10 to the minus 11. This is unitless, by the way. Okay, even though the m didn't cancel out fully, the equilibrium expressions are always unitless. So Kb equals 6.8 times 10 to the negative 11. It's a very weak base. Okay, the next part is calculate Ka for glycolic acid at 25 degrees. So again, based on my equilibrium expression up here, I know that here Kb is, since we calculated 6.8 times 10 to the minus 11, and I need to find this Ka. So in this Bronsted-Lowry, because water is my other part of my Bronsted-Lowry equation, I actually know the equilibrium constant for water at 25 degrees. It's a constant. Kw equals 1.0 times 10 to the negative 14. So if there's actually an equation I can use to solve for the Ka of my glycolic acid, and that is Kw equals Ka times Kb. So we can rearrange this. So Ka will equal Kw divided by Kb. Okay, so that will equal, Ka is 1.0 times 10 to the minus 14 divided by 6.8 times 10 to the minus 11. Ka, again, I'm going to round it to 2 sig digs. Hopefully this is right. It's 1.48 times 10 to the minus 4, but I'm going to round this to 1.5 times 10 to the negative 4. Okay, that's how I solved the Ka question. And then finally in question 7, I'm shown a reaction mechanism of how to produce methyl glycolate, and I'm shown step 1 and step 2, and I'm being asked, is H3O hydronium a catalyst for the reaction? So yes, it is. We can see that it's a reactant over here in step 1 and then a product in step 2. So the definition of a catalyst is that it has to be a reactant first to speed up a reaction. In this case, that would be step 1, and then it's a product after. So catalysts are also recycled. So what that means is, as a product in step 2, it's now available to come back and cycle back to another step 1 in the future to catalyze and speed up step 1. So I'm going to say that I agree, because the definition of a catalyst is H3O plus appears as a reactant first in step 1, which will speed up the reaction, and then it's produced as a product in step 2. Now, another key aspect of this definition is, notice that this canceled out. It's not in my overall reaction, so that's true for definition of a catalyst. It will not appear in the overall equation because it's not a true reactant. So additionally, so again, mine is a little wordy. You can check the answer key later. H3O plus does not appear in the overall reaction. Okay, and this is consistent with catalyst definition. Okay, and also remember that intermediates are similar. They also are canceled out, but intermediates are products first, then reactants. So they're produced and consumed, so they also get canceled out. So catalysts and intermediates, those are similar in a mechanism, but this is the definition of a catalyst, and hopefully this is right. Please put any questions, disagreements, or comments in the comment section. Thank you so much for watching.